Welcome back to the Hyperbolic Coding Chamber. This is day 41 of LeetCode Every Day. Reflections on yesterday, we carved a video called The Process of Deforestation Continues. And that's just a pun because, the problems that we're focusing on were tree problems. So we're trying to get a ton of those done, which I think we have. So feeling relatively okay there. And so I guess the point, right, with practice, the greatest gains lie in our weakest areas. So hoping to actually graphs are actually where I'm pretty weak, so I got a tip from the old copy ninja about the special subset data structure called a union find, right? And so we've been working on this union find / disjoint set data structure, right? And it's pretty cool, I guess. One thing that it allows us to do, it allows us to test connectivity in a graph pretty straightforwardly, right? Directly or indirectly, right? And there's a couple of optimizations you can use, right? You can use the optimized disjoint set, right? So this would be for quick union, because you can either optimize for quick union or quick find, right? In the case where you optimize for quick union, find can devolve to linear time amortized. Linear time, but the average time complexity with Ackermann's inverse function, which I don't really know what it means, is constant time for that, as well as the quick union, which would also devolve to average constant time complexity, but in the absolute worst case would be linear time if we use ranking as well. And so we've kind of been going through this Explore card, and this Explore cards are actually pretty useful. So they're pretty much showing us how to use the disjoint set data structure. And so we have a bunch of problems lined up. We actually were able to do a problem maybe 1 or 2 hours ago called number of provinces, and that was pretty cool because it was pretty cool to see how being able to test connectivity allows us to know a couple of things, right? And so number of provinces really allowed us to see that the way to solve that problem is to throw it into a union find data structure, right? And then we'll have our root array. And then from there, we can just check how many different root nodes do we have, and that would be the number of provinces, right? Because we want to know pretty much how many clusters there are. And it turns out that there is just one cluster, right, in the problem that they're giving us when we start. So union find, very, very, very useful. Hoping to osmosis the code line for line into my brain so we can use it and pull it out any moment at any time. Right. That being said, to get to that point, we have like 6 problems lined up, and it's part of the disjoint set Explore card, so we know that we're going to be able to solve these problems with union find. That being said, though, the mechanism by which we do solve it using union find, we are going to need an intuition behind how the data structure works to be able to actually get a solution. One version of that we noticed was with number of provinces. So we're going to need an actual understanding of these data structures, right? We can't just memorize the lines of code and then use them. So this Explore card is going to be very helpful because it's just going to allow us to know what are the general markers of when we should try and use this, right? And what are the general markers when we should avoid it, right? And so I'm hoping that we can get through these six problems today with an hour and a half. But we shall honestly see. We will not actually know. But that being said, we grokked the data structure pretty quickly, which is a good sign. And then hoping to finish out the graphed subtree of the Explore card, right, with DFS, BFS, right, MST, which is probably something we really need to know how to do, and topological sorting, which is a recurring topic, especially for a problem called course schedule, right? And that's a problem we're actually stuck on. So that being said, I'm also noticing, due to a tip from the copy ninja, that supplemental reading is actually very, very important. I noticed that a lot of the tips and tricks I'm noticing are from application, which is important, which means we can osmosis intuition and long-term, wisdom from doing these problems. But it's actually even faster, and we build those knowledge graphs in our head even faster with supplemental reading, which is what I'm noticing with this Explorer card. So thinking that we should have started this sooner, supplemental reading, but it is what it is. We can only play the cards that we were given. We can only play the hand that we were dealt. So it is what it is. So what I'm thinking from here is that going to solve or try to solve graph valid tree. And if we can do that, we'll do number of connected components, then earliest moment when we were all friends, and so on and so forth. And this is actually the wrong order. So I'm gonna slow down. So let's slow down. I'm talking really fast. I want to go too fast for the problems, make extra mistakes. And it's really about how good our practice is, right? So let's jump into that. So you have graph valid tree. You have a graph of n nodes labeled from 0 to n minus 1. You are given, so if we have n nodes, we'll have, let's say we have 5 nodes, we'll have 4 nodes total. No, we'll have n nodes, but they'll be labeled 0 through 4. Okay. You're given an integer n and a list of edges where edges sub I is equal to a sub I and b sub I. Indicates that there is an undirected edge between nodes AI and BI in the graph. Return true if the edges of the given graph make up a valid tree, and false otherwise. So I guess it would make up a valid tree, right, if all the nodes could be connected into one tree, right? So a node where couldn't form a valid tree, so it's undirected, and we see here that this is not a valid tree because 1 is connected to 3 and 3 is connected to 2, so it's actually not that simple. There are no self loops or repeated edges. This is interesting. So a graph of n nodes labeled from 0 to n minus 1. We're given an integer n and a list of edges where edges sub I is equal to a I b I. So edges is actually an array of tuples, right? So we have n equals 5 and we have our edges 0, 1, 0, 2, 0, 3, and 1, 4. So that's actually really convenient because typically, right, with union, find, or disjoint set, right, we want to be able to access, we want, you know, a tuple of edges, right? So this is interesting. If we were to do union find on this particular graph, right, we could be able to see that all of the nodes, right, would have one root node, which would be 0, right? Which makes sense. I guess the problem would be, right, if we had an edge between 1 and 2, right? If we had an edge between 1 and 2, that would be a problem. Right, which is what we see here. So let's create this in what this would look like in our union find, right? So we'd have our edges 0. We can just copy our edges from here. I'll make this just a little bit bigger. Actually forgot to start the timer. But we'll just assume that we're about 5 minutes in. So we'll have this edge here, which we will copy into our problems right here, right? And if we were to add all these edges into our union, right, union find data structure, right, our array would look like this, right, going from 0 to n minus 1. We'd say, is there an edge between 0? We'd say there is an edge between 0 and 1. Right, so 0 would be our root node, right, for itself, and these would all start like so. And then for 1, we would change its root node to 0, right? And then for 2, we would change its root node to 0. For 3, we would change its root node to 0. And for 4, we would change its root node to the parent node of 1, right? Which would actually be, or we could just change it to 1 like so. And so the root nodes of all of these would be 0, right? So if we were to do the same for this graph below, right, where is our problem case? If these are our edges, right, we would have 0, 1, 2, 3, 4, and then we would have 0, 1, 2, 3, 4, right? 0 would be the parent node for index 0, right? We'd have an edge between 1 and 2, right? And so we'd set 2 equal to 1, right? And then we'd have an edge between 2 and 3, and we'd set 2 equal to 3 here, and we have an edge between 1 and 4, and we said we just set 4 to 1 here like so. So we have basically one too many connections. Our root node here still ends up being 0, but our problem being that we don't want multiple connections between nodes. So if we create a connection between 2 and 3, right? I guess if there's ever a node with an out degree, it's undirected, so that's actually kind of tough, where no self loops or repeated edges. So how would this be different with our union find data structure? Has to be a method to the madness. We'd have 0, 1, with an edge between 0 and 1, 1 and 2, then 2 and 3. So let's check if this makes sense. For index 0, right, our parent is 0. For index 1, our parent would actually be interesting. So we have 0, we have 1, 1 here. Edge between 0 and 1, right? So we'd want to set 1 equal to 0. Right, 1 equal to 0. And then from here we'd have 2 and 1. We have an edge between 2. So we have 1 and 2, right? So we said 2 equal to 1. Then we have an edge between 2 and 3. We said 3 equal to 2. Edge between 1 and 4, we said 4 equal to 1. So if we find the root node for 0, it's going to be 0. The root node for 1 is going to be 0. The root node for 2 is going to be 0. The root node for 3 is also going to be 0. So if we were to rearrange this, we can see that this has a tree structure, which means that we have connections to nodes, but then we have connections from our connections to nodes. Here we have a connection to 1, right? But there's a connection that goes from 1 to 3. There are 2 connections that go to 1. We have a similar thing here with 0, so that seems fine. These connections. I guess another way that we can see it is that they're saying there are no self loops or repeated edges. However, you could go from node 3 to 1 to 2 to 3 to 1, 2 to 3. So we could know if it's a graph if there's a loop, basically. If it could be a graph of n nodes, right? Make up a valid tree. If it makes up a valid tree, right, there would be no loops. This actually does indeed have a loop. So could our union find tell us if we have a loop? We have a loop between 1, 2, and 3. So maybe we could take this from a different angle, right? Because we're having trouble using the union find. Maybe we could take this from a DFS angle and just visit our neighbors. Right, maybe we could visit our neighbors, and if we visit our neighbors, we'll be able to tell if there is a cycle in the graph. So let's try that. Right, to tell first, one way we can visualize a graph is with an adjacency list, right? And so our goal would be to have 0 to 1, right? And then 1 to 4, 2, and 3. Right, and then 4 to an empty array, 3 to 1 and 2, right, and then 2 to 1 and 3, right? So that would be our goal. Right, so we're going to need a map to create this, and this map would be a key of number, right, to an array of numbers. And so how could we load this tree up with these how could we create this adjacency list? Right, so we'll just call it edge. So we could iterate over edges, right? And so we'll say for const edge of edges, right? We're gonna want to check if the starting edge, right, exists in the map, right? So if map dot has edge sub 0, right, then what we want to do is push on the edge, right? But only if it does. So if map has the edge, right, and then we're going to say const r equals map dot get edge sub 0, right? We're going to say if r, right, does not include edge sub 1, right, then we're going to do r dot push edge sub 1, right? Now if it doesn't have the edge, what we want to do is do map dot set edge sub 0, right, equal to an array which is going to have edge sub 1 in it. And so we should have our adjacency list here at this point, right? And they want us to return true or false, so we'll return false to start just to print our adjacency list. We're going to need to basically remove all of these comments that we made. So let's run the code and see if our adjacency list makes sense to start. We changed it to adjacency, so let's change our map. So you have 0, 1, 2, 3, right, 1 to 4. oh, it's this one right here, right? 0, 1, 2, 3, and 1 to 4, right? So this makes sense. All right, so we have our adjacency list. Now I want to make sure there's no cycle, right? So to do that, right, we're going to start with our first node. So we'll say, we can do this recursively, right? And so we can just say, search. So what we could do is do a return of search, right? And this search would be done DFS style. So we'd say DFS search, and what we would pass in, right, would be the adjacency list, right? And our starting node, right, which would be, we'll just take the first key as our starting node, right? And we're going to pass in, right, a set, right, which is going to be a number, right? And this is going to allow us to make sure that when we visit, when we finally find, if we ever see a node twice, then we're going to make sure that if we ever see a node twice, then that means there is a cycle. So to go in, right, we're going to need our adjacency list, which is a map of number to number array, right? And we're going to have our cur, which is going to be a number. We're going to return a Boolean, right? And from this point, the goal would be to visit the neighbors, right? And so to visit those neighbors, what we would like to do, is do, oh, and we're missing cur. We also need our set, right? We're going to call it visited. It's going to be a set, right, of numbers. We're going to say if visited.has cur, right, we're going to return false. Now, if it doesn't have it, right, what we want to do is do visited.add cur, right, and then what we want to do, right, is visit all of our neighbors, which is going to be all of the values in this array for this particular index, right? So we're going to say our neighbors are actually going to be equal to map.get of cur, right? And we're going to do for each so we actually want to return a tuple. I mean, we actually want to be able to string this together, right? So we can return true, right? And we can do dot sum here, right? So to visit every neighbor, right? We'll say neighbor, right? And we'll do DFS search with adjacency lists, right? N, right? And visited. Right now, if one node, right, actually allows us to find the value, right? Allows us to find the value, then we're going to return, we're going to around this, basically this whole sum out to be a true. And so this is actually a little bit all over the place now that I'm thinking about it. So for a particular node, we'll go from 0, right? We'll say if visited has cur, right? 0 is not in the set, right? So we do add 0, right? Then we're going to return true and visit all the neighbors. So we're going to do DFS search of 1. Is 1 in the set? No, so we add 1. Then we're going to visit neighbors of 1, and then we're going to say, okay, return true and, right, check if 4, right? And 4 is not in the set, so we add it and then we return true, and then neighbors is an empty array. So if we get the neighbors, right, it's map.get of cur, right, if neighbors.length equals 0, right? So if we have no neighbors, right, then we'll just return true, right? So when we get to 4, we'll have no neighbors, return true, go back up to 1, right? Our sum will be true and true, go back up to 0, right? Will be good so far, and then we want to visit 2, right? 2 is not in the set, so we add it, right? But its neighbors is equal to 0, so we return true, then we visit 3, right? And so sum does at least return true. So I think we actually want to change this to every, right? So that every one of them returns true. And then I think this should work, so let's try it. We're still using map. We want to use adjacency because adjacency is the name of our map. Right, and if this, we want to only do this if neighbors actually exist. It's possible neighbors doesn't exist. So if neighbors doesn't exist, right, it's actually going to give us false. Right, and this is actually, you only want to do this if neighbors, right, if not neighbors or neighbors dot length equals 0, then we want to return true. Otherwise, neighbors exist. And we misspelled neighbors, I think. We have an extra H. So let's see if this meets our time complexity. So we actually fail here. So our output returns true. Is it 0, right? Our map would be 2, 1 to 3, 2 to 3, and 1 to 4. So it's actually not a cycle that we can immediately tell from looking at this. So we know that there's an edge between 0 and 1, right? And then 1, an edge between 1 and 2, edge between 2 and 3. There's an edge between 1 and 3. So this would actually be a cycle. There's also an edge between 1 and 4. This would actually be a cycle. So this should only return true if every single neighbor turns true. So let's actually see what our map ends up being. Our adjacency list, I mean. Two, then we go to 3, and then we go to 2, right? 2 goes to 3, then we go to 3. Undirected, so I think the way we're creating our map is actually the problem. We set an edge between 0 and edge between 1. But we actually want to create an edge between both. So we create, if edge has edge 0, right? And so we actually want to add both edges into the adjacency list, and I think this would fix our issue. So quickly fix it. I mean, duplicating this wouldn't be the ideal solution, but we'd say if edge, if the adjacent list has this edge, right, then we would get the value of that edge, right? And if R doesn't include the value of edge sub 0, then we push edge sub 0. Otherwise, edge sub 1 would be the value of edge sub 0. So our output is still true. So our map actually makes more sense now, because we would have edge between 2 and 3 and edge between 1 and 3. So this actually does make sense now, but our way that we're checking for neighbors is a little strange. We're making sure that every neighbor, we visit every neighbor. We want to make sure if visited does not have cur, right? If visited has cur, then return false. Otherwise, we add it. Then we want to get the neighbors. Now, if the neighbors don't exist, or the neighbor's length is 0, we return true. Otherwise, we want to return neighbors, right? Now, if every neighbor, if we're able to visit every neighbor, the depth first search, it could be that we're returning false where it's not propagating correctly. So another way to do this, let's just do for const n of neighbors. Right, and then here we'll do return the DFS we'll get a value, right, and we'll say if DFS, right, then we'll return false. Otherwise, at the bottom here, we'll return true. And visited. We're still getting true somehow. So let's just follow this through. We have our map. Where's our console? We have our map here, which is 1, 0, 2, 3, 4, and then 1, 3, 2, 1, and 1. Right, we're starting a depth first search with the first key, right, which is going to be 0. Right, so we're going to say, does visited have 1? It does not. So we don't return false, and we add 1 to visited. Okay, then we have the neighbors, right? So we want to get the neighbors, which is 1. So the neighbors does exist, so for n of neighbors. So we're going to do a depth first search of the adjacency list with n, which is now 1, right, with visited. So now we're visiting 1, right? Is 1 in the visited? No, so we add it. So now we have 0 and 1. And then we get the neighbors of 1, right? The neighbors is not empty, so we're going to do n of neighbors. So now we're at 0, right? So now we're visiting depth first search of 0, right? We're going to say if visited has 0, it does, so we should return false. So something's off here. It should be returning 1. Since once we get back to 0, we'll have visit, we'll have created a loop. Maybe what we want, no, well, if we visit the first key, right? Once we visit it, we say if it has cur, we return false, right? So maybe let's just print visited I wonder if we're returning here. No. So we're getting no neighbors for key sub 0. So something is off here. I wonder if cur is our key value not making sense. So our key value isn't making sense. We did add.keys sub 0. What you should be able to do, you do add.keys. Right, if we print that value, you get an iterator. So I guess you can't subscript it. So what you'd really want to do is actually do add.keys, spread it into an array, and then pass it in. So now we're getting the correct value. So as between 0 and 1, 1 and 0, output is false. Zero and 3, this will not actually would be valid because it would be the array from earlier, which would be 2. And so maybe we actually don't want this double case here. So you have a range from 0 to 1 and 2 to 3, and yeah, right. So this is why we want union find, because neither of these are connected to the same elements, right? And we actually have no way of checking that in our current implementation. So we have to use union find somehow. So now that we've gone this far with it, right, how can we use union find? So we know that there's one case, right, where nodes are not connected to the same root node, right? If they're not connected to the same root node, that's a problem. It can't be a valid tree, right, because it's incomplete. The other case is when we have a cycle. And how do we know if we had a cycle? How would we know if we had a cycle? If we have, for example, node 3 and we visit its its parent node, right? Then we could go from a parent 3 parent node to 2, right? And from 2 we would go to 1. Then from 1 we could go to 0. So how do we show that these nodes are creating a loop here? Maybe we could use our original solution from before and union find together, but that seems a little messy. So 0, 1, 2, 3, and 4. How could we use them in unison? Well, we don't want to use them in unison because union find would allow us to know that two nodes are not connected to the same root node, which is a problem. And if they are connected to the same root node, we have a problem if there's a cycle. Maybe if we visit, so maybe we could actually do a check, right? So let's just say we do check that all the nodes are connected to the same root node. That's good, right? Then we want to make sure, right, that there's no cycles iterating through the graph. So from 4 we would go to 1, or right, from 4 we'd go to 1, right, and from 1 we would go to 0, and from 0 we'd go to 0, so that makes sense. From 3 we would go to 2, right? From 2 we would go to 1, from 1 we would go to 0, from 3 we would go to 1, from 1 we would go to 0. So actually, let's implement the union find data structure and see, because it's hard to know if our value here of our vertices to root nodes is mapping up correctly. So let's actually implement it and see if the solution will show itself in the construction of the map, in the construction of the root array. To do that, we could implement a class called quick union, right? And we'll optimize it with the root array, which is going to use a compressed path, and also with rank, which is going to help optimize quick union. And so we'll call these root and rank. In our constructor, right, we're going to take a number of vertices, right, and based on this number of vertices, we will load our union find data structure. Right, when we start, these values we're going to want them to be set to themselves, right, in regards to the root array. So we do root.push, right, I, right, but rank, we all want them to start at a rank of 1 because their height is going to be 1. So this dot rank sub I is going to equal, or not I, we're going to say this dot rank dot push 1 to start, and then we're going to need the find function, right, which is going to take a index, right? It's going to output a root node, which is going to be a number, and to do that, we're going to say let x equals index, right? And we're going to continuously search upwards until x, which is the index, is equal to the value at the node itself, at the node itself. So while x does not equal this dot root sub x, right, we want to do x equals this dot root sub x, right, and then we'll return x. And then for the union function, right, we're going to take x, right, component x and component y. We're not going to return anything, right? Well, first we need to get the first root, which is going to be root x, right, which is going to be this dot find of x, right, and root y, right. We're going to find the root node of x and y, right. We want to make sure, you only want to do work if they're not the same, right. So if they're not the same, then we want to use our ranking to optimize the quick union, right. And so to do that, we'll say if the ranking of root x is greater than the ranking of root y, that means that x's rank, x's tree, is of a greater height. If that's the case, then we can actually add, right, this dot root sub root y would actually be equal to root x. So we can actually add root y as a root. We can actually attach root y subtree to x, root x at no extra cost since our tree is greater than it. And we're going to say if this dot rank sub root root y is greater than this dot rank sub root x, then we want to do the opposite, right? This dot root sub root x is going to be equal to root y, right? So if the rank of root y is greater than root x, right, we want to set root x equal to root y. Otherwise, right, they're the same height. And if they're the same height, then we can just, doesn't really matter which one we choose, but we'll just choose to duplicate our first version, right, when root x is greater. So we'll say this dot root sub root y gets set to root x, and then we'll upgrade the rank of root x plus equal 1. And so to check if something is connected, right, we're going to be able to do this in about constant average time, right, with component x and component y, right. We'll say if we can just return this dot find the root component for x, right, and if it equals the root component of y, then we're in business. So now we just want to load, right, this quick union data structure, and the number of edges it's going to have is going to be n, the number of vertices as mentioned by the problem, exclusive of n, and then from here we just want to load the edges, right, into the quick union data structure. So we'll say const edge of edges, right, and we'll say qu dot union, right, edge sub 0 and edge sub 1. And then here we'll actually just console.log qu.root to see if there's any method to the madness, and we'll return true just to appease TypeScript. We're needing a semicolon on line 7. All right, so our root node for all of these nodes is 0, which makes sense, and our output is true. Right, our output is indeed true. Now let's print the ranking as well and see if there's anything we can use in there. Right, so if there is a cycle, so maybe if all the root nodes, maybe it's indeed the version of this, since the version that we're using is actually the root node version. Maybe we could change this, right, so we have the connected version instead, rather than the root node, we'll just have the parent node instead. And so instead of returning x, what we'll return is this dot root, so index. So root is still here, and so right, root is x and root is y. So what I was hoping for was that in our final one, instead of connecting 4 is 0, 1, 2, 3, 4. 4 should actually say 1 instead of 0, but it says 0. So x equals index. We just want to return, instead of having it hold the root, we'll actually just have it return its parent index, which would be roots of index. Then we're checking if the roots aren't the same. And so actually a simpler version of this, right, we won't actually optimize for rank, but we'll do is we'll actually do the union, right? We'll set this dot root sub y will actually be set to the root of x, and then I think we should get what we're looking for. Oh no, not root x. We want to set it to x. So the root of x. So what we're seeing here is that 1 has a parent node of 0. 0 has a parent node of itself, and then 1 has a parent node of 0. 2 has a parent node of 1, which it shouldn't. So this, I think this version is actually too simple. I think what you would actually do is this would take linear time, because you would iterate over I equals 0, I is less than this dot root dot length, I plus plus, and you'd say if it's not roots of I equals y, right, then you would change this dot roots of I equal to x, not the root of x, just x. So I think this makes more sense. So we have 0's parent is 0, right? 1's parent is 0, which makes sense. 2's parent shouldn't be 1, it should be 0. So 0, 1. So we're just setting it to 1, right? Right, and then 1's parent, right, is 0, which makes sense. And then we have 3, 0, 1, 2, 3. 3's parent is 2, and 2's parent is 1, and 1's parent is 0, and then 4's parent is 1. So we'd still like to return true in this case. So what if we uncomment our original case, right? And the output we were getting then, actually we need to uncomment this as well. Right, so this actually makes sense. What about this version, right? So if we put in, or this version is the version, right? So we'd have, I'm seeing now, okay, so the last version, okay, so the last version was actually this version. How could we use maybe we were onto something originally by fusing the depth first search, which would check if there was a cycle, and union find, which would check if the trees were all connected. But wondering if there's a way to do that with the union find data structure without having to use another one, well, actually having to implement the adjacency list again. So actually we copy this and we roll our change. Actually, we can copy the whole thing. We roll our changes back to the adjacency list version. So then this version should work but fail on a future case. Then what we'll do is at the top here, we'll print our other version, and this valid tree here, go all the way to the bottom. We'll paste it down here. We'll remove this, the extra return true. What we really want to check here, once we load our union find in, right, what we want to check is that all nodes connected, and we can check that by doing qu.root, right, .every, right, we can say indices, right, and for every indice, or I guess the easier way to do it would be, so let all nodes connected equal false, right, and what we'll do is, actually we could do it like this. So we'll say root nodes, right, will equal a new set, right, of numbers, similar to what we did before, and we'll have qu.root, right, and we'll have for each, right, index, we actually want to do root nodes dot add, right, qu.find the root node, right, for I. And so you want to return the DFS, right, of this, right, which is going to make sure there's no cycle, and that root nodes dot size equals 1. See, this is our original example. We actually return false. We still have our double case in here. We do. Forgot to remove that in our rolling back. So we get stuck on a larger case. So maybe it's not as simple as checking if there's no cycle and all the nodes are connected to the same root. Maybe the problem is not that simple. Let's see a hint. Given n equals 5 edges, 0, 1, 1, 2, and 3, 4. So let's turn this into a tree. Let's turn this into a graph. I have 0 to 1, 1 to 2, right, and 3 to 4, right? And so we know this isn't a graph because it's not completely connected. That's what our union find structure helps us check. And if it's a tree is an undirected graph in which any two vertices are connected by exactly one path. In other words, any connected graph without simple cycles is a tree. So that's what we're going for. So maybe the way we check for cycles is incorrect. Any two vertices are connected by exactly one path. Vertices are connected by exactly one path. So I'm thinking the way that, this is why we're doing graph review, I'm thinking the way that we actually, this is another problem we have with a different problem where The way we were checking for cycles using a graph was just not optimal and also didn't make sense. So if it's connected, that's how we can use the quick union. But if without simple cycles is a tree, so where are we failing here? We have 5 to 6, 0 to 2, 1 to 7, 5 to 9, 1 to 8, 3 to 4, 0 to 6, 0 to 7, 0 to 3, 8 to 9. Now this is not a graph. Wonder if they have the tree viewer. Without simple cycles, so how can we tell if a graph has a simple cycle? The way we're going about checking if our graph has a simple cycle is incorrect. And no cycles. So what we're giving is integer n, a list of edges where edges of I indicates that there is an undirected edge. Since it's undirected, it means you can go back and forth. If you go to 0, if you go from 0 to 1, it means you can go from 1 to 0. Right, but that actually gives us a false positive. You also go from 0 to 2, 0 to 3, and you go from 3 to 0, which makes sense. But if we say 3 has a neighbor of 0, then we'd actually end up returning false. But in this case, we don't have any false positives because we have 0 to 1, 1 to 2, 2 to 3, and 1 to 3. There are no self loops or repeated edges. Yeah, I think we just have trouble checking if there's a cycle in a graph. We minimize our quick union class. We have a valid tree n. So we should just visit. We should just check why this is failing. Need a way to draw this. Wish LeetCode had a built-in drawing mechanism. Let's see, 5, 6, 0, 2, 1, 7, 5, 9, 1, 8, and this is impossible to visualize. So I have an edge between 5 and 6. 0 and 2, 1 and 7. You also have a node between 5 and 9. Alright, then we have a node between 1 and 8. Then we have a node between 3 and 4. We have a node between 0 and 6. Node between 0 and 7, and node between 0 and 3, and 8 and 9. So I think the most important thing that I'm noticing here is that this graph is actually not, if we connect 1 to 7, I think it is connected actually. It's kind of hard to visualize. 5 and 6, anyone connect, oh, it does connect to 6, it's undirected, which means yeah, this is tough to visualize. So I take a second to draw something. If there is a cycle, this is what we should be working with. If this is our tree, the problem is we know that all the nodes are connected, which is good. The problem is that the way we detect if there's a cycle is erroneous. So this is the same issue we had with a different problem. And there's a way that we're checking for edges that just doesn't make sense. So we iterate through this. Let's just check what our adjacency list looks like. So our adjacency list looks very, very simple. Oh, we need to pass it in this version. So let's check if this matches. We have 5 going to 6 and 9, right? 0 going to 2, 6, 7, and 3. 2, 6, 7, 3. Right, 1 going to 7 and 8, 1 going to 7 and 8, right, and then 3 going to 4, then 8 going to 9. So we're missing some edges here, and I think this has to do with what we had earlier, where it's undirected, so we should be able to go I think I see what might be the issue. If we do a DFS only starting from the first node, right, we want to check if there's a cycle. So we're doing this DFS, we're testing if there's a cycle. Our output is true, there is a cycle. So what we want is that if there's no cycle, that's right, if there's no cycle, but I'm seeing that we still want one more thing. And there's if no cycles, right? And to do this, what we actually want to do is do add.keys spread into an array. We want to do every node. We want to make sure that there's no adjacency list. Or if there's at least one cycle, so has some cycle, we basically want this to not be, to be if it doesn't have some cycle. if it does not have some cycle, right, it'll be add, right, the keys that we're sending in. We can remove this. Key will be n. So this should still give us a good answer, right? When we run it for all of them, maybe we'll be good now. So even if we run from 1 to 4, right, we're returning false. If at least one of these returns true, if we have at least one cycle, this will return true. We want to have no cycles. So if one of these returns true, it'll be true, otherwise it'll be false. So we're actually returning false. So we visit 1, has no neighbors, return true. Right, and so now I'm noticing if it has no neighbors, we actually return true. So our logic is just all over the place. If it has no neighbors, right, we want to return false. And this is a problem with pretty much how we name this. We call this as cycle. And then we could change return true to return. If it, we've seen this before, we want to return true. If it doesn't have neighbors and neighbors equals length, then we'll return false, right? And if it has a cycle, then we'll return true. Otherwise, we'll return false. So we run this, we actually get our output true. At least one of these has a cycle. Nine doesn't exist. 2 doesn't exist. 6 doesn't exist. 7 doesn't exist. 3 doesn't exist. We go to 3, we go to 4. 4 doesn't exist. Got neighbors, right? Neighbors like 0, then return false. It doesn't have a cycle. Has cycle visited, then we want to return true. Yeah, the way we're, our way we check, way we check. Yeah, this is, we're just all over the place with this one. We just need to check if the graph has a cycle, and we are incapable of doing that. Maybe we could do a simpler version that has cycle, a level order traversal, which we'll implement down below. It's probably our last try for this. We have this set up, and so we want to do our level order traversal. Which means we're going to start our queue with the JSON-C.keys, right, of the first key, right? We're going to start our queue with, and we're going to say while queue.length is not equal 0, right? And we're just going to check here, right, if it doesn't have, if it has a cycle. So we're going to have visited, which is going to be a new set of number. Right, so we're going to say const cur is going to be q.shift. All right, we're going to say if visited dot has cur, right, return false. Otherwise, we want to keep going, so we're going to push our children. All right, so we get const neighbors equal JSON clist dot get cur, right, and we'll say if neighbors, right, or and neighbors dot length does not equal 0, right, then we want to do neighbors dot for each n, right, q dot push n, right, and if the visited doesn't have cur, right, then we want to do visited dot add cur, right, then we want to visit the neighbors, right, so we're going to push all of our neighbors on and then go to the next iteration. So check if that makes sense. We push 0 onto the queue, right? If visit has 0, it doesn't, so we'll push 0 into visited. Then we'll get all our neighbors, right? Our neighbors do exist, which would be 1, 2, and 3, and then we'll push them all onto the queue, right? So now we're going to put 1 off the stack. Well, does 1 exist visited? No, we add 1. Then we get the neighbors for 1, right? We push that onto the queue, right? Then we pull 2 off. This 2, have we seen 2 before? No. Add 2, then we pull 3 off. Has we seen 3 before? No. We add 3, it has no neighbors. Then we pull 4 off. Have we seen 4 before? No. It has no neighbors. So let's see if this makes sense. This still returns true. So let's print visited afterwards. So we only visited 5, 6, and 9. So I'm thinking what we want to do is maybe load all of the keys into the queue to start. So it looks like this does work, but it's very, very, very slow. It actually doesn't even print. We actually return false here, so we visit 0 and 1. Well, let's print our so it doesn't even get to print visit because we end up exiting, right? Peer visit has cur, right? So this is actually our starting one, which is here. We end up returning false 0, 1, 0, 2, 0, 3, and then 1, 4. Right? We end up visiting every node. Putting all the keys in, we do eventually revisit them. especially when we get to 1, 4. No self loops or repeated edges. There are no self loops or repeated edges. There are no self loops or repeated edges, but this is a self loop right here. Oh, there's no self loops on particular nodes, but there are loops. Neighbor's neighbor not equals 0, then we push the neighbor to be handled. In this case, we end up visiting. We push all the keys to start. We'll always pretty much return true then. But what key should we start with then? Oh, the root. But the root is, in this example, visit all the nodes, right? We wanted to start with the root node. So to do that, we could actually do, if we use our union find from here, before we do our level order traversal, the root node would actually be root nodes size is not equal 1, right? And we want to return false already because that means that we aren't connected. We make it all the way down here, we can just return true. And so we want to actually set the root node to be the highest node, which would be root node dot keys should be the first element, and we'll actually just print the queue to start to see if that makes sense. We met root nodes. Oops, this is a function. I really thought that was it. So this is strange. If our set is actually 6, we do qu.root.for each, right? We add all the root nodes. Root nodes dot size. Wait, what is going on? Root nodes dot size should be 0, especially if we're doing qu.find. So root nodes.size not equal 1 should return false. Let me just double check this. All right, so root nodes is 1. Well, we have a set here. Oh, that's because we're printing visited. Output is true, we expected false. Same one from before. We're just not good at telling whether or not we run into a cycle. Visited has cur, we want to return false. Otherwise visited.add cur. We can take a look at the adjacency list as well. I mean, for this particular case, right, 6 doesn't exist. Then we go to 9. Six doesn't exist. I think we're only visiting half the tree. I think we need to do what we did earlier, but maybe not as simple. I think the method by which we're loading elements into the graph is nonsensical. It's very one-sided. We produce 5 to 6, but it's undirected, so why shouldn't we add an edge from 6 to 5? I think we can actually, except now we'll be iterating through this through the root node, so we shouldn't actually run into ourselves again. So if edge does not have edge sub 1, right? Then we want to get edge sub 1, and if the array doesn't include edge sub 0, then we want to add edge sub 0. So that's what's set edge sub 1 equal to edge sub 1, edge sub 0. All right, so in this case, so our root node is still 1, but we do end up running into ourselves. Even if our root node is 0, set ends up being what we don't want actually is the else case. So our map is 0 to 1, 2 to 3, right? 1 to 2, we output false. They want us to return true. Edge between 1 to 2, right? 3 to 1, and then 1 to, so edge between 0 and 1, right? Then 2 to 3. So we have 0, 1, 2, 3, and then 1, 2 up here. That's the case, and there shouldn't be a cycle, right? Because if we go from 0, we visit 1, right? Then we visit 1, and we go to 2. We visit 2, we go to 3, and then 3, we'd go to 1, which would return false. Oh, I don't understand.